In mathematics, the complex conjugate of a complex number is the number with equal real part and imaginary part, equal in magnitude but opposite in sign. For example, the complex conjugate of 3 plus 4i is 3 minus 4i. In polar form, the conjugate of rho e I phi display style rho e caret I phi is rho e minus I phi display style rho e caret I phi. This can be shown using Euler's formula. Complex conjugates are important for finding roots of polynomials. According to the complex conjugate root theorem, if a complex number is a root to a polynomial in one variable with real coefficients, such as the quadratic equation or the cubic equation, so is its conjugate. Notation: the complex conjugate of a complex number z display style z is written as z display style overline z or z display style z caret asterisk closing curly bracket. The first notation, a vinculum, avoids confusion with the notation for the conjugate transpose of a matrix, which can be thought of as a generalization of the complex conjugate. The second is preferred in physics, where DAG is used for the conjugate transpose, while the bar notation is more common in pure mathematics. If a complex number is represented as a 2 times 2 matrix, the notations are identical. In some texts, the complex conjugate of a previous known number is abbreviated as C. Quote, for example, writing E I phi plus C display style E caret I phi plus text C closing curly bracket closing curly bracket closing curly bracket means E I phi plus E minus I phi display style E caret I phi plus E caret I phi. Properties: the following properties apply for all complex numbers z and w, unless stated otherwise, and can be proven by writing z and w in the form a plus ib. A significant property of the complex conjugate is that a complex number is equal to its complex conjugate if its imaginary part is 0. That is, if the complex number is real. For any two complex numbers w, z plus w equals z plus w, z minus w equals z minus w, w equals w slash w equals slash w. If slash w is defined, z equals z r n equals n z pipe equals pipe z pipe 2 equals z equals z equals z minus 1 equals z pipe 2 z does not equal 0. Display style begin aligned overline z plus w and equals overline z plus overline w overline zw and equals overline z overline w overline zw and equals overline z overline w overline z w and equals overline z overline w. Quad text: if w text is defined overline z and equals z tilde left right arrow tilde z in mathbar r overline z caret n and equals left overline z right caret n quad for n in mathbar z left overline z right, and equals left z right, left z right, caret 2, and equals z over line z equals over line z over line z, and equals z caret minus 1, and equals frac over line z left z right, caret 2. Quad foral z, neq 0, end, aligned. The penultimate relation is involution, i.e., the conjugate of a complex number z is z. The ultimate relation is the method of choice to compute the inverse of a complex number if it is given in rectangular coordinates. Exp z equals exp z. Display style exp over line z equals over line exp z. Closing curly bracket backslash closing curly bracket log z equals log z. Display style log over line z equals over line log z. Closing curly bracket backslash closing curly bracket. If z is non-zero, if p display style p is a polynomial with real coefficients, and p z equals 0, display style p z equals 0, then p z equals 0, display style p over line z equals 0 as well. Thus, non-real roots of real polynomials occur in complex conjugate pairs. See complex conjugate root theorem. In general, if phi display style phi closing curly bracket is a holomorphic function whose restriction to the real numbers is real valued, and phi z display style phi z backslash closing curly bracket is defined, then phi z equals phi z display style phi over line z equals over line phi z closing curly bracket backslash closing curly bracket. The map sigma z equals z display style sigma z equals over line z closing curly bracket from C display style mathbar C closing curly bracket to C display style mathbar C is a homeomorphism where the topology on C display style mathbar C is taken to be the standard topology and antilinear. If one considers C display style mathbar C closing curly bracket as a complex vector space over itself, even though it appears to be a well-behaved function, it is not holomorphic. It reverses orientation, whereas holomorphic functions locally preserve orientation. It is bijective and compatible with the arithmetical operations, and hence is a field automorphism, as it keeps the real numbers fixed. It is an element of the Galois group of the field extension C/R. Display style mathbar C mathbar R. This Galois group has only two elements: sigma display style sigma closing curly bracket and the identity on C display style mathbar C. Thus, the only two field automorphisms of C display style mathbar C that leave the real numbers fixed are the identity map and complex conjugation. Uses a variable. Once a complex number z equals x plus I y display style z equals x plus e, or z equals rho e I theta display style z equals rho e caret I theta is given, its conjugate is sufficient to reproduce the parts of the z variable. Real part x equals re z equals z plus z 2. Display style x equals operator name re z equals dfrac z plus overline z 2. Imaginary part y equals im z equals z minus z 2 I. Display style y equals operator name im z equals dfrac z overline z 2 I. Modulus or absolute value rho equals pipe z pipe equals z z. Display style rho equals left z right equals sqrt z overline z. Argument e I theta equals e I arg z equals z z. Display style e caret I theta equals e caret I arg z equals sqrt dfrac z overline z. So theta equals arg z equals 1 I lane z z equals lane z minus lane z 2 I. Display style theta equals arg z equals dfrac 1 I lane sqrt frac z overline z equals dfrac lane z lane overline z 2 I. Furthermore, z display style overline z can be used to specify lines in the plane. The set is a line through the origin and perpendicular to r. Display style overline r. Since the real part of z r display style z cdot overline r is 0 only when the cosine of the angle between z display style z and r display style overline r is 0. Similarly, for a fixed complex unit u equals exp bi, the equation z minus z 0 z minus z 0 equals u display style frac z underscore 0 overline z underscore 0 equals u determines the line through z 0 display style z underscore 0 in the direction of u. These uses of the conjugate of z as a variable are illustrated in Frank Morley's book Inversive Geometry, 1933, written with his son Frank Weiger Morley. Generalizations. The other planar real algebras, dual numbers, and split complex numbers are also analyzed using complex conjugation. For matrices of complex numbers, a b equals a b display style overline mathbf ab equals overline mathbf a overline mathbf b closing curly bracket, where a display style overline mathbf a represents the element by element conjugation of a display style mathbf a. Contrast this to the property a b equals b a display style mathbf a b caret asterisk equals mathbf b caret asterisk mathbf a caret asterisk, where a display style mathbf a caret asterisk represents the conjugate transpose of a display style mathbf a. Taking the conjugate transpose or adjoint of complex matrices generalizes complex conjugation. Even more general is the concept of adjoint operator for operators on possibly infinite-dimensional complex Hilbert spaces. All this is subsumed by the asterisk operations of C** algebras. One may also define a conjugation for quaternions and split quaternions. The conjugate of a plus b I plus c j plus d k display style a plus by plus cj plus dk is a minus b I minus c j minus d k display style a by cj dk. Note that all these generalizations are multiplicative only if the factors are reversed. Z w equals w z display style left zw right caret asterisk equals w caret asterisk z caret asterisk closing curly bracket. Since the multiplication of planar real algebras is commutative, this reversal is not needed there. There is also an abstract notion of conjugation for vector spaces v display style v over the complex numbers. In this context, any antilinear map phi v display style phi v right arrow v closing curly bracket that satisfies phi 2 equals id v display style phi caret 2 equals operator name id underscore v closing curly bracket, where phi 2 equals phi display style phi caret 2 equals phi circ phi and id v display style operator name id underscore v closing curly bracket is the identity map on v display style v closing curly bracket phi z v equals z phi v display style phi z v equals overline z phi v closing curly bracket for all v display style v in v closing curly bracket z c display style z in mathbar c closing curly bracket and phi v 1 plus v 2 equals phi v 1 plus phi v 2 display style phi v underscore 1 plus v underscore 2 equals phi v underscore 1 plus phi v underscore 2 backslash closing curly bracket for all v 1 v display style v underscore 1 in v closing curly bracket v 2 v display style v underscore 2 in v closing curly bracket is called a complex conjugation or a real structure, as the involution phi display style operator name phi is antilinear. It cannot be the identity map on v display style v. Of course, phi display style operator name phi is a r display style mathbar r linear transformation of v display style v. If one notes that every complex space V has a real form obtained by taking the same vectors as in the original space and restricting the scalars to be real, the above properties actually define a real structure on the complex vector space V display style V. One example of this notion is the conjugate transpose operation of complex matrices defined above. It should be remarked that on generic complex vector spaces there is no canonical notion of complex conjugation. See also complex conjugate vector space, composition algebra, real structure, Wirtinger derivatives. Notes: Budenich, P. and Trautmann, A. The Spinorial Chessboard. Springer Verlag, 1988. ISBN 0-387-19078-3. Antilinear maps are discussed in section 3.3.